Hey everybody, today's lesson is 3.5. You guys, today we are going to be graphing those crazy looking functions with those weird dotted lines, and we have a bunch of new vocabulary words, one of which is an asymptote, which is this word right here. I'm going to give you a little time to get all of this stuff copied down that I already have filled out, so you might want to pause the video, copy stuff down. I am going to go right into example 1, referencing all of this stuff and this down here. As I'm kind of doing this problem. So what we have to do is graph number 1, and there's a lot of steps that we have to follow in order to get a graph for this crazy looking function. So pause the video if you need to, get all this stuff copied down, and I'm going to go right into doing number 1 based on what we have written down here. So very first thing that we have to do for this problem is we have to set the denominator of this problem equal to 0. So what that's called is finding the vertical asymptote. It says to find, set denominator equal to 0 and solve. And what an asymptote is it's a dotted line on the graph and the function does not go through it. So I like to explain what asymptotes are to my students as my mom has 2 dogs that are trained on an electric fence. So if you've ever seen a dog that's trained on an electric fence, what they do when you walk past their house is they run right up to that electric fence line, and you can't see it, but it's there because it's going to zap them. As you know, if they go through it, it's going to give them a shock on their collar. So these graphs are going to work a lot like those dogs do, where they approach that dotted line, which is called the asymptote. They approach their fence line, but they never go through it. So think about an electric fence in terms of what an asymptote is. So I'm going to zoom in kind of on this first problem. Very first thing I'm going to do is exactly what they told me to do to find the vertical asymptote. Set the denominator equal to 0 and solve. That means that I have x equals 2. This is my vertical asymptote, and I'm going to abbreviate it VA. And so what I have to do on my graph, usually I like to use a red dotted line, but I am going to put an electric fence on the line x equals 2 on my graph. So what that looks like is here. So I'm just putting the asymptotes, or the fences, on my graph. It's a vertical line, x equals 2. Okay, I'm going to be doing a lot of zooming so I can kind of like reference back and forth to what we're doing here. So that was finding the vertical asymptote. That is the first thing that you do for graphing these functions. The next thing we're going to do is find the horizontal asymptote. And as you can see, that to find the horizontal asymptote, we have 3 options. And so option number 1 is if the degree of the top is less than the degree of the denominator, which in this case that is not true. This is not case number 1. But if it was, my horizontal asymptote would be the line y equals 0, so I'd put a dotted line right here. This problem, number 1, falls into case number 2 here. The degree of the top is just 1, and the degree of the bottom is also 1. So in that case, I'm just taking the lead coefficient of the top divided by the lead coefficient of the bottom. So what I'm going to do there is I'm going to write that work out to the side. I'm going to do horizontal asymptote for this one. So my horizontal asymptote is the line y equals, the lead coefficient of the top is 1 and the lead coefficient of the denominator is 1, which just means y equals 1 is my horizontal asymptote. So again, I'm going to put a red dotted line at y this time equals 1. So think about horizontal asymptote, that's a y equals line. So that needs to go this way. I'm going to do it in red. So you can kind of see my dotted line, my fences, that I'm putting up for those dogs. Okay? So they're dotted lines and the graph is not going to cross them. And so notice how what I wrote for number 3, if the degree on the top is greater than the degree on the bottom, which is not this case, we're actually going to talk about that in a couple days. That is your oblique asymptote, OA or slant asymptote, and we will talk about that in a couple days. So all the ones we're going to do for the first couple days are case number 1 or case number 2. Okay, so far I haven't done anything for my graph. All I have done is put the asymptotes on there. But let's find the x-intercept and the y-intercept. So what I'm going to do is do that part down here. The y-intercept is telling me to plug in 0 for x and solve. So my equation is, you know, the f of x is just a fancy y. So if I plug in 0 for x, I get 0 plus 1 over 0 minus 2. I'm just using this equation right here, plugging in 0 for x. And so what that's going to give me is 1 divided by negative 2, which is negative 1/2. So that means that the y value of my graph is 1 comma negative 2. That's the y-intercept. That means where it crosses the y-axis. So where is the point 0, comma, negative 1/2. So what this means is my y-intercept, if I want to write it as an ordered pair, that means I have 0, comma, because I plugged in 0 for x, and when I did that, the y value was negative 1/2. That point is right here. So far I have 2 asymptotes for my graph and a point. Okay, well that is not that helpful, but let's do the next one. So for x-intercept, what that says is plug in 0 for y. And so remember that the y is the f of x, that means y. So if I set my equation equal to 0 and I actually cross multiply, the denominator is going to go away, and really what I'm doing is setting the numerator equal to 0 and just solving that. Okay, so I'll do that in green. What that means is I'm going to take the numerator of my equation, which is just x plus 1, and set it equal to 0. So the numerator is here, that's the x plus 1, and set it equal to 0 and solve for x. So that means that x equals negative 1. So that means that when I plugged in 0 for y, I got negative 1 for x. So that ordered pair goes right here, negative 1, comma 0. And so far, you guys, here's the cool part, is that what I need to do at this point is I'm going to connect those dots. And this is a crazy looking graph. We kind of did a little bit of that already in our activity that we did in class a couple days ago. But what I'm going to do, if you remember the fact that these dotted lines, these asymptotes, are kind of like electric fences. The dogs are playing in the yard, and the graph is going to approach the electric fence but not go through it. So if you have those asymptotes on your graph, it helps you figure out what the shape of the graph is supposed to look like. The dogs are drawn to the edge of the fence line because they want to play in their yard, but they're not going to go through that fence. So right now what I've done is I've gotten half of my graph. And what I could do here is actually make this a little bit thicker. Here's the first part of the graph. So all I have to do now is, the problem with this graph is I have no idea what's happening on this side of the asymptote. I know on this side of the asymptote my graph is right here. So I need to jump over the other side of the fence, and I need to see what these dogs on this side of the graph are doing. So what I need to do is pick any of these x values over here and plug it into my equation just to figure out if my graph goes like this or if it goes like this. Okay, so all I'm going to do there is I'm going to pick one other point. I think I'll pick x equals 3. You could also pick x equals 4, x equals 5, any x value over here on this side of the asymptote, the vertical asymptote, just to get one more ordered pair to finish my graph. So I think what I'm going to do here, I'm going to do this off to the side. Oh, my pen's still pretty fat. Okay, I'm going to choose x equals 3 and plug that into my equation. So that means that y equals 3 plus 1 over 3 minus 2, which is 4 over 1. So when I plug in 3, I got 4. That means that 3 comma 4 is another point on my graph. So go to 3 comma 4 on the graph, which is right here. Put a point there, and that tells me that to finish my graph, it looks like this. No, you don't need any other points on the graph because the asymptotes help you do the graphing, because the graph is going to be attracted almost like a magnet to those asymptotes but not go through it. Okay, so that, my friends, is a rundown of everything that you wrote for number 1, all of those words and stuff, and how to actually apply that to the graph. Always need to find vertical asymptote and horizontal asymptote and put those on the graph. Then do x-intercept and y-intercept, put those on the graph. And then you might need to choose other points to complete your graph. Just keep in mind, the more points you choose, the more accurate your graph will be. Then you just connect them. Let's talk about domain and range real quick before we move on. Just look at the asymptotes. That's really all you need to know. These graphs are continuous except for those asymptotes. So the domain of my graph, it's every value, every x value, except, where's my asymptote for the x value? My asymptote's at 2. So how do you write the domain of every single number except for 2? That means I go negative infinity to 2 and 2 to infinity. And why are they parentheses and not brackets? Because the graph does not touch the asymptote, so you can't include 2. I'm going to actually make a little note about that. The graph does not touch 2, so use parentheses. Okay, not brackets. So for the range, we're going to do almost the exact same thing. The range is all the y values except for, look at where the y equals asymptote is. So the range is every y value except 1. So that means negative infinity to 1 and 1 to infinity. Okay? So they're kind of like long problems. I'm going to do 2 more on this video, and then we're going to do the last one in class together. So I'm going to breeze through the next 2 examples, doing everything. If you get lost or something, refer back to this page, because I'm just going through this page one at a time, and then putting all the points together and graphing. Alright, so let's look at this example. Here we go. I'm going to fill in all these boxes first, and I'll kind of go back and forth between the graph and the boxes. Just kind of referencing what we're doing here. So remember, the vertical asymptote, that means set the denominator equal to 0. That is how you find the vertical asymptote. So that means that 4 equals 2x. That means that x equals 2. So there's my vertical asymptote. I'm also going to do the horizontal asymptote here. If you refer back to the first page, this is a case where the degree of the top is 0 and the degree of the bottom is 1. So when the degree of the top is less than the degree of the bottom, by definition, what you have written down on the first page is that means that the horizontal asymptote is y equals 0. What I'm going to do now is put both of those on my graph. X equals 2 is here. Here's my dotted line. And y equals 0 is the x-axis. So I've got my electric fences all set up and ready to go. So that's the first thing that you want to do for your graph. Y-intercept, that means plug in 0 for x. So that means I get 6 over 4 minus 2 times 0, which means 6 over 4, which is 3 over 2. Remember, I did that by plugging in 0 for x. So I got 0 comma 3 over 2 when I plugged in 0. So I'm going to put that on the graph. 0 comma 1.5 is right here. There's my y-intercept. I'm going to do the same kind of thing for the x-intercept. What that means is set the numerator equal to 0. So that means that I set 6 equal to 0. Can't do it. That means that there is no x-intercept. And so let's think about why that makes sense for a second. Why is there no point on the graph that falls right here? Why is there no x-intercept? Because I have an asymptote there. The dogs can't go through the fence. Okay, so that actually makes sense mathematically why I don't have an x-intercept. I'll do domain and range after I get everything plotted. Okay, so I have 1 point already on my graph, and I know what the graph is going to do. It's going to be attracted to those electric fences. So this section is going to go this way and run up along the fence. This section is going to go this way and run up along the fence, but it's not going to go through it. So I've done one section of my graph already. I know that there's nothing down here, because for sure these are functions, you guys. They still need to pass the vertical line test, but I need to know if my other swoop, I refer to these as swoops, is on this side or if it's on this side. So I need to pick an x value over here on the x-axis. I'll pick either 3 or 4 or 5, it doesn't matter which one you pick, but pick a point over there just to fill in the rest of your graph. So I'm going to choose when x equals, maybe I'll do 4 this time. So that means that I am going to plug in 4 to my equation, and it's weird that it's staying there. It's okay. So that means when x equals 4, I need to fill in what the ordered pair is going to be. I'll do that work down here. So I get 6 over 4 minus 2 times 4, which is 6 over 4 minus 8, 6 over negative 4, which is negative 3 over 2. So where is that point? 4 comma negative 1.5? That's like right here. Okay, cool. So that means that the other part of my graph goes in this direction. Okay, so now let's do domain and range. The domain is every single x value except this asymptote, and the x value here is 2, so every single x value except for 2. Negative infinity to 2, 2 to infinity. Remember, it doesn't touch 2, so you have to put parentheses on there. And then the range is every single y value except 0. So it goes down forever, it also goes up forever, but it doesn't go through 0. So I'm going to do negative infinity to 0, and 0 to infinity. Okay, and that's how you complete that graph. Let's do one more. And then we're going to save number 4 for class tomorrow. Alright, vertical asymptote. Set the denominator equal to 0. That gives me x equals -1. Horizontal asymptote. The degree on the top is the exact same as the degree on the bottom, so I'm taking the lead coefficients. And be careful because these are both written out of order. So the lead coefficient is actually -2 on the top, and the lead coefficient of the bottom is 1. So I'm doing y equals, the lead coefficient of the numerator is -2, lead coefficient of the denominator is 1. So I have two different lines to graph as my asymptotes. The first one, x equals -1, that is an electric fence line that goes right here. And y equals -2 is an electric fence line that goes right here. So I got my asymptotes ready to go. Let's do y-intercept. That means plug in 0 for x. So that means I get 6 minus 2 times 0 over 1 plus 0, which is 6 over 1, which is 6. Okay, so my y-intercept is way up at 6. 1, 2, 3, 4, 5. It's a little bit off the graph, but that's okay. X-intercept, set the numerator equal to 0, which means 6 minus 2x equals 0. When you solve that, you get x equals 3. So if you wanted to put these in ordered pairs, the y-intercept is 0, 6. The x-intercept is x equals 3, 0. So those are the actual ordered pairs if you want to write them like that. I would prefer that actually. Okay, so those are the 2 points for this section of the graph, and I know it's going to be attracted to the asymptote but not go through it. Same thing here, it's going to run up along the asymptote but not go through it. And how about, I need to get one other point. I know that there's no graph down here because that would make it not a function, but I need to know if the other half of my graph is in this section or if it's in this section. So I need to pick one of these x values just to complete my graph. I think I'll do -2. You could also do -3, -4, -5. I'm going to do -2. So I need to figure out what happens when I plug in -2 to my equation. That means 6 minus 2 times -2 and 1 plus -2. So when I complete that, I get 6 plus 4, which is 10, and 1 plus -2, which is -1. So -2, -10. That's not really on my graph, so I could do the same thing for -3. Just as an FYI, when you plug in -3, you can verify this if you want, but you get -6. That's probably an easier point to graph. -3, -6 down here. I would give you a better graph so that these would actually fit on the graph. But again, now that I have that one point, I know that my graph is going to approach the asymptote this way and this way, but not actually go through it. So the two sections of my graph look like that. Let's do domain and range real quick. The domain is every single x value except for, it goes left forever and right forever, except it doesn't go through -1. So -infinity to -1 with a parenthesis because it doesn't go through it, -1 to +infinity. The range is all the y values except for this one right here, -2. So -infinity to -2, -2 to infinity. We will do the last one in class tomorrow, you guys. I know that was a lot, but every single one's the exact same. You just have to memorize those steps and how to find everything. And once you find everything, it translates into the graph. Just keep thinking about that electric fence. Your graph is going to be like a magnet towards the electric fence, but not go through it, okay? Thanks for watching. Have a good night.